What is up everybody, I'm Ritvik Dashwara and I'm back with a video and some new learnings. In this video we are going to do our first Monte Carlo simulation and we will be performing some option pricing valuation. That is, we'll be finding the call and the put premium price through Monte Carlo simulation. Before starting this video, I would like to have a small request. If you have not yet subscribed to my YouTube channel, then please smash the subscribe button and hit on the bell icon. Also, if you want to use my codes for your personal uses, you can actually go to my YouTube channel. This is my YouTube channel, and click on this button, which is access to my Google Drive. It is basically a Google Docs form, and I will be requiring some basic information like your name, your email address, and I'll be giving access of my personal Google Drive to that particular email address. Also, you have a different channel name, then just mention your channel name here. By saying channel name, basically whenever you subscribe, it comes. I can see your channel name as my subscriber, not your name. So if you have a different channel name, then just please mention that that particular channel name. In most of the cases, it's your actually full name. So also, don't worry about spamming from my side. I'm a student. I don't have that much time. I'll be using your email address just to give access to my Google Drive, and you can use all of my codes for your personal uses. There is no copyright issues. I am making this code for all of you guys only. It's free for everyone. The one and only condition that has to be fulfilled is that you have to be my subscriber. So yeah, first click on the subscribe button and then click on this button to get the the access to my Google Drive, and then enjoy all my codes for free. Anyways, so let's start with our motive of this video. Now, we are doing Monte Carlo simulation in this video. The underlying principle of Monte Carlo simulation is to use the randomness to solve our problems. So what it does is it basically creates a lot of paths, and we go from one point to another point through a lot of different paths. And at the next point, at the observation point, we actually check all the outcomes of these particular different paths, and then we do the analysis. This is basically the very basic definition of Monte Carlo simulation. So what we are doing is we are using the randomness to solve our problems. In this case, in order to make this randomness, I'll be using geometric Brownian motion. So it means that I'm assuming in this model, I'm assuming that the logarithmic of prices follows the Brownian motion. Now, Brownian motion is a concept of physics, and basically it means that if we have, for example, if we have a box and it has a lot of gas molecules or liquid molecules, let's consider gas molecules. So Brownian motion is basically the motion of one particular gas molecule inside that box. So it will be colliding with any other gas molecules, and it will have a random motion inside that box. That motion is actually the Brownian motion. There is a formula in order to get it, and I have written it in a very good handwriting in the MS Paint. So this is basically the formula of geometric Brownian motion that I'll be using. There is a proper derivation for this formula. It's quite complex, and I would say if you are not a physics student, there's no need to learn the derivation of it. And if you want to learn it, just go Google it. I am from physics background. I know how to derive it, but I don't think that there is any need to do it right now, right here. So I'll be just using this formula in order to get this randomness, and then we'll be doing Monte Carlo simulation on all those random paths that we created. Okay, so let's start it. Again, we are doing options pricing here using the Monte Carlo simulation. So what are the inputs that we are required? First thing is the spot price. For example, the spot price is 100. The second thing required is what is the time period of that option. Let's consider 1 year. The third thing is what is the discount rate that we'll be using in order to price that to price the call and the put option. So let's take 7% for example. What is the volatility of that particular stock or that underlying security that we have for that option? So sigma, which is volatility, which is standard deviation, and let's take it to be 0.2, that is 20%. Now, oh, I'm sorry, I just put 2 is equal to here. Okay, that's it. I think yeah, that are the things that are required. Now, in order to make the Monte Carlo simulation, we need to have the number of simulations that we that we require in order to get the final output. The more the number of the simulation, the better. But if I will put, like for example, 1 million or 10 million simulations, then in that case my code is has a lot of chances to get crashed. So what I'm doing here is I'll be using just 5,000 simulations, 5,000 simulations. And yeah, one more thing to do. What I'm doing here is I'm taking daily movement of the stock price, and in 1 year we have 250 trading days, right? Approximately 250, it's 252 or sometime 253, but approximately 250 trading days. So what we'll be doing is, like, we will be getting that the daily pricing through the Brownian motion, and then through those daily movement we'll get the final output, that is the price after 1 year. And then, because this is an option, this is not a forward, what we'll be doing is we will calculate the payoff of call and payoff of put at that time, at the end of 1 year. That is the maturity time. And if the payoff is negative, we won't exercise the option. So it will be the maximum of I would say, in the case of the call, it would be the maximum of the spot price at that time minus the strike price. Strike price is basically the price at which we exercise the option. In call, if we buy the option; in put, we sell the option at the strike price. So it will be the maximum of S, which is the spot price at that moment, minus the strike price. And in put, it's the other way around. It is K minus S. So we'll be calculating the payoff at that time, and then we will discount it back for this entire 1 year, and we'll get the present value of the payoff, which is actually the call and the put premium price. We'll be discounting the payoff using the continuous discounting. You can use other methods, but I'll be using continuous discounting here. Now, okay, so I'm sorry. So from first, like from t is equal to 0 to t is equal to 1, we have 250 days. So we would be having n steps is equal to 250. This is the variable that I'm taking. Now the important thing to do is we will be, as I already mentioned, we'll be doing the Brownian motion for the daily prices. So dt is basically t divided by n steps, right? Simple. Okay, now this is the formula that I'm using for the Brownian motion. So let's start making it. So in this formula, let's first try to understand what is this formula. In this formula, what I'm doing here is, this is basically the stock price at time t is equal to 1. This is the stock price at time t is equal to 0. And how are they related? They're related by with this expression, and this is actually the exponential of this, which we also call as a drift. This is the time component, which is a here. I just took it a. And this is the random variable that I'll be using here. The random variable follows the normal distribution, the standard normal distribution, which is actually having the mean of 0 and standard deviation of 1. And this is the drift, and this is the time component. So let's make all these things one by one. Drift is equal to r minus sigma square divided by 2 star dt. Perfect. A is equal to sigma star square root of this. Perfect. So for that I would need NumPy library. So we have drift and we have A. Perfect. Now we need the random variable. Let's take random variable to be x. This is random dot normal with the mean of 0 and variance of 1, and we need this random variable to have, you know what, I should make it 5 and 2, sorry, 5 and I would say 4. Let's take 5. So like I'm not putting 5,000 and 250 for now, because I'll be like checking all these things in order to see that I'm not making any mistake. Because if I put 5,000 and 250 here, I won't be able to see the output, because like it will be huge array and I won't be able to check it. Okay, so what I need to do is I need to make a random matrix of n simulation cross n steps. So let's see, it's not working. N simulation np dot random dot normal 0, 1, and simulation is 5 and steps. Okay. Perfect. So we have the random matrix of 5 cross 5. If I take it 4, so we can see that these are the number of simulations on y-axis. On x-axis we have the number of steps. If we have 1 year data, it should be 250, like on the x-axis, and if we increase the number of simulation, that should be 5,000 or 10,000 or whatever you write it. So we have the random variable here. Let's keep the output here for now. Okay, perfect. So now let's make our matrix of S, which is the movement at the stock price. So let's call it SMAT. Perfect. Let's make a zero matrix first. SMAT is equal to np dot zeros and simulations comma and steps. Okay, let's keep on checking it. SMAT is this. Perfect. Now so yeah, this is like on the y-axis you can see that we are doing 5 simulations, and on the x-axis these are the steps. So in this case we are just having 4 steps. If we like after some time I'll do it 250, because the number of steps are basically 250. We have 250 days in a year, but for now I'm having just 4 steps. Because these are 5 different simulations, we should have 100 on all the first element of all these small arrays, because at t is equal to 0 the price is 100. So let's make it 0, on the 0th element, which is this one, it should be S. Perfect. So from the second time period, which is actually t is equal to 1, we will have to use the geometric Brownian motion formula in order to get these different paths. In this case we are doing 5 simulations, so we'll have 5 different paths. Okay, so let's start making let's start using the Brownian motion formula in order to get the 5 different paths here. So I'll be using this formula here, the Brownian motion formula. Okay, so for I in range of 1 comma n steps 𝐻𝐼 I is equal to 1, then take the price, the last day's price, which is 𝐻𝐼 comma I minus 1 np dot, we have already imported numpy, okay, np dot exp, then drift plus a multiply by this random matrix, which is okay. So estimate I this colon comma I think it should work. Yeah, it should work. So let's see what is our estimate. Perfect. So we have 5 different simulation for the value of for the price of the stock price. Perfect. So we can see that in the end we have 5 different outputs. 2 are less than 100 and 3 are more than 100. Now our next thing to do here is to calculate the payoffs for call and put. So for that, let's first of all see what is the strike. Okay, so I forgot to mention the strike price. Let's say strike price is 100. Shift enter. Okay, so if the strike price is 100, the payoff for call is say Q. So that would be 𝐻𝐼, the last one, which is minus 1, and then minus K. No, I did some mistake here. Perfect. So we can see the 1 2 3 4 5 1 2, okay, this 1 1 2 3 4 5. Perfect. Yeah, so we can see that the first 2 payoffs are negative and the last 3 payoffs are positive. Because this is an option, we cannot have a negative payoff, so let's just eliminate this negative payoff. So I'm making a small for loop here for I in range len of Q, which is basically 1 2 3 4 5 here. So it will take Q I, no, if Q of I is less than 0, then what to do is Q of I is equal to 0. If it's greater than 0, then Q of I is equal to Q of I. Perfect. So we can see that these first 2 are now zeros. Similarly, for that we need to have the payoff of for put as well. So for put, say P, and payoff of put is K minus the spot price at that moment. So I, and then let me just do it quickly. So yeah, so we have the payoff of put as well. Now payoff F of call would be basically mean of Q, and payoff of put would be mean of P. Perfect. I think it's right now. Now what we need to do here is discounting it back to the today's price. So call is equal to payoff of call multiplied by np dot exp. As I already mentioned, I'm doing continuous discounting, which is minus r multiplied by t, because now t is 1 year, and put is equal to payoff of put. Let me just copy it. So this is the call and the put prices. Now you can see that we just had 5 simulation and we used 4 steps, which is not the right thing. Let's increase it, and then what we'll be doing is we'll be comparing it with the Black-Scholes model, and we'll see that are they similar or is there a huge difference. There should not be a huge difference. So let's see if we are right or wrong. Let's do 5,000 simulation, and n steps is basically 250 that we already talked about. Now I need to remove these things because I don't want to execute these things because it will be huge array. SMAT is done, Q is done, P is done. You can see the payoff of call is this much, payoff of put is this much, and then call and put prices are 11.74 and 4.76. The call price is 11.74 and the put price is 4.76. Now let's compare it with our Black-Scholes model that we did in in one of the last videos. If you have not watched how did I do this, how did I make functions of Black-Scholes model, just click on this I button and you'll see there's a video that I already made, which is this one. And yeah, we did all these things, and in the end we got the call value and the put value. So now let's see in our case what is basically the price that we get through the Black-Scholes model. So in our case we use S is equal to 100. I'm looking into here, this one, all the parameters that I need to provide, all the inputs that I need to provide. Okay, S is 100, K is also 100, R is basically 0.07 in this case, volatility was 20%, and time was 1. Let me just copy it. Perfect. So using the Black-Scholes model, we got the value of call to be 11.54, which is not very different from 11.74, and the value of put to be 4.78, and in our case we have 4.76. It's very close. If I increase the number of simulations, let's make it 50,000, it will be even more close. 11.41 and 11.54. Like we can see that there's a very minute difference in the Black-Scholes model, which is a theoretical academic model, and the Monte Carlo simulation, which is basically the one of the very important simulation that is done in the industry. And we can perform a lot of like processes using the Monte Carlo simulations. This is one of them, like doing the options pricing through the Monte Carlo simulation. But we can also do a lot of things apart from options pricing theory using the Monte Carlo simulation. It is one of the most useful simulation that is being used in the finance industry. So yeah, I hope you liked my video. I'll post this code on the Google Drive. If you want it, you can just, first of all, you subscribe to my YouTube channel and then click on my on this button on my YouTube, I would say YouTube page or YouTube channel, whatever we call it, and then I'll give you the access to my Google Drive. I hope you like this video. Thank you so much for watching this video. In the next video, I'll be doing linear programming and using one of the most useful library, I would say, which is Pulp for linear programming optimization. So I hope you watch my next video as well. Thank you so much in advance. See ya.